Welcome. Welcome to the Design++ seminar series in the spring semester 2025. My name is Andreas Müller. I'm one of the co-leads of the Immersive Design Lab at Design++. Design++ itself is the Center for Augmented and Computational Design in architecture, engineering, and construction, with several goals on its agenda. One of the main goals was and is the knowledge transfer, which we, let's say, try to foster through lectures, through workshops, and also through different summer schools, in a sense. And one of the key platforms that we have here is actually the seminar series itself. It offers different possibilities to introduce speaker with topics which go beyond the things that we would see here, actually. So which go beyond the classical approaches from lectures that we would have here. With this said, it's now my pleasure to introduce you today's speaker. Not too long ago, he was actually standing here. Thank you. Not too long ago, he was actually standing here at my position as the co-lead of the Immersive Design Lab. Before that, he was a postdoctoral researcher at the Stanford University and is now, from April 2024, an assistant professor for structural engineering at the TU Darmstadt, focusing on computer-aided methods and artificial intelligence in particular. His talk will explore shortcomings of traditional data-driven approaches of machine and deep learning and structural analysis, and introduce research work towards agentic systems in this area. Please welcome with me, Prof.Dr. Michael Kraus.
So yeah, good evening, everyone. Feels like homecoming. It's really nice to see a lot of known faces. So I wanted to report a bit on what I did in the past year when moving away from the ETH and having the new opportunities in Darmstadt. And actually, my first slide, I was inspired by one of the first talks we had in that series, because for me that I think gave the notion that usually we talk about crisis. We have environmental crisis, economic crisis, war, expulsion, and so on. And I think these kind of stories, they emphasize a need that we have to tackle, for example, climate change. But I think that we have to see these things in the light of what civil engineers do and how they do it. Meaning that we want to establish safe and reliable structures which are resilient and economic, and even stronger in that sense, sustainable. So I think that is megatrends which force how we deal with our daily business in civil engineering, coming up with infrastructure, doing some design and analysis. And my special field of, okay, that did work. My special field of the professorship is structural analysis, which is very close to what I did here in the ETH. So what is the core tasks of structural analysis? And how do they relate to the crisis and the megatrends which drive our daily business? So the first of the three core tasks in structural analysis is to support the design by doing pre-design and pre-dimensioning, and I think that is the most trickiest part, develop realistic structural analysis models for that design. So I quote here Walter, he always says it's very good to have mechanically consistent models, and I think that reflects here this first important core task of structural analysis. The second one is to actually solve these equations which we come up with. That means we choose a suitable computational method, do the analysis and the computation, and then the important step is control what we have done. If that makes sense or not, using some estimates, rule of thumb, or offset calculations, and then correct. So the second core part in structural analysis or core task is conduction of the analysis and or computation and analysis and the evaluation of that. After that, the third core task comes into play, which is actually the transfer of our structural abstraction of the computational model to things which are built. And we have to verify them by design standards and so forth. And that is all the basis for the assessment of reliability, the modification of the initial design in case of refurbishment, or the monitoring. So keep these three core principles or core tasks in mind, because I will structure and relate the current computational methods in structural analysis to these three things, because they are in common. That is what our profession as structural engineers drive, at least for the structural analysis part. Short intro or thing what I do in Darmstadt. I'm driven by these three things. So you see that modeling, analysis, and construction. And from my predecessor, I inherited three groups mainly, which is dealing with glass, dealing with paper and snow and avalanches. And my special group, which I founded new, is this analysis and AI. But what have these three groups in common? They all deal with model building, numerical analysis of that, and then translation of that models and designs into actual constructions, or vice versa, look at constructions and come up with modeling or analysis approach. And I think that is also what I share with the people I met here. That has to be a good agreement or a good optimum between doing fundamental research and being applied enough so that we can actually translate these things into practice. So if you're interested, I can talk a bit more about that, but today we will just look into that area here, because that is, so to say, which I'm most active at the moment. So remember the three core tasks in structural analysis. So if we look into this first task, abstraction and modeling, to get an impression of how long it took people to come up actually with the methods which we use and even teach in everyday classes in structural analysis. That's interesting that in the antiquity until the Middle Ages, people dealt a lot with approximation methods like approximating pi or other things. And then in the 70s to the 19th century, there was this formalization of mechanics. So mathematicians came and took the ideas from the first mechanicians and turned them into equations or tried to formalize that. And that ended in the early 20th century in famous first concepts like the graphical statics, which was researched here in the ETH by Professor Kuhlmann, and the matrix methods, which were driven by even civil engineers, and all the numerical methods for solving of the PDEs, which we use today. So the timeline here says roughly 4,000 years to come up with matrix methods and graphical statics. And then we have 1 century of computation. So we are still with this task of computation and analysis, so the second core principle in structural analysis. So the first one took around 4,000 years to be formalized. Now, what is with the actual analysis? So that took a year, and I think that this rapid speed up in development of these numerical methods for analysis, that was driven by a megatrend, namely energy stability and the increase in well-being and welfare of the community. And an example, I don't want to advertise here nuclear power, but I think that is a very impressive example for how construction could be increased in terms of dimension by enabling through, for example, the finite element method. So that means 1 century, 100 years roughly, where people started with first matrix methods until they came up with modern state-of-the-art finite element methods. Again, here for the people who know adheres, Clough, and Zientkowski, they are all, and Zuse, they are all civil engineers, and I think that were main drivers for that. Funny side fact, with the upcoming of the computational methods, also first ideas or first steps in the machine and deep learning, they happen simultaneously to that. So 4,000 years for coming up with formal methods in mechanics, 100 years in getting to numerical modern computational programs and software. What about the AI? What about machine and deep learning here? I'm showing work which I have done with colleagues here at ETH mainly to set a bit the context here. So first, applications of these methods are, for example, data-driven. So we have a data set on a specific type here, network arch bridge, and then we use some older methods to come up with this cluster, and then the cluster would inform us about similarities which these bridges share in different coordinates, which I showed here. Another thing where machine and deep learning is used or was used historically is surrogate modeling, meaning fitting a model, a formula, so to say, to data, and then being able to or extrapolate. And the latest wave is still a thing which tries to get the best out of the theory world and the data-driven world, which varies under different or lives under different terms. I called it here physics-based AI because I have worked a bit on that. And here the idea was, can I train my neural networks to respect differential equations, which I know from the mechanics, for example, and I can combine this with data, but I don't have to. I can just synthetically train that to fulfill, for example, Euler-Bernoulli beam theory. You look at this and you realize, okay, that is additional methods, what traditional machine deep learning does. That's additional computational approaches like the FEM, but other kind of algorithms. And my hypothesis for today, which I would like to trigger a bit the discussion, is I think that this does not help in the upcoming 2 mega trends much. So because they're passive tools, right? So we use the computer with a software to conduct a task like doing structural analysis. But I think there is 2 mega trends, labor shortage and the increased need for sustainability, which for me means even more computations, optimization, and investigation of variance. And I would like to propose to you an idea about using autonomous AI agents and explain or report a bit on our first steps in that direction. And as I said, so that should or would, in my eyes, trigger a bit of a discussion if that is the solution to that. So what's the motivation for seeing it in that perspective, that all this surrogate modeling, classical machine and deep learning, that is a passive thing and we need to do something active. So we actually get support by intelligent agents. That, in my eyes, is because what is an engineer doing today? In the end, it's a transformer of information. The engineer gets some documents from the construction site or from the architect or the stakeholder of that building and then transform that kind of information, maybe in text form or as visuals, into technical documents. So basically it's a translator, and the translation is possible because that person has been educated with technical content and then with some experience when dealing with that projects. So this translation aspect gave me the idea for, okay, a multimodal language model basically does the same. It translates from different modes of information, for example, text mode, image mode, voice mode, whatever mode, to another mode. And the question or the research hypothesis here is, can we actually create an agent, and is it one agent, to get into that loop of doing these three core basic tasks of the structural analysis: the abstraction, the numerical analysis, and the translation to a design. Yeah, so that's the experiment what I want to present a bit today. Before that, I was not sure if everyone is on the same page about the language I use. So allow me to present two slides just to introduce what is a large language model. So basically, you can think of that as a very big neural network having a transformer architecture, which is trained on a very vast amount of data. So if that is an original LLM, then it's just text. And you can think of an LLM as a regressor over text, right? So it would not be like a regressor where you put in your number of balls and whatnot. You would put in text and then it would regress, so to say, with some probability, the next word. And what is a multimodal LLM? Yeah, that means I'm not only regressing text, I'm also regressing audio, images, videos, could be BIM files, whatever you think of. So that's one component which we will heavily use, an LLM or LLMs. And the race of that LLM being trained on a vast amount of data gives rise to what's called in-context learning. So that is the ability of an LLM to perform new tasks without having to retrain that model, without parameter updates. And I only need instructions or an example input-output, which is called a prompt, to get the response of that. Okay, so if you remember my regression example, so if I want to use the regression model for another task than what it was trained for, I would have to retrain with new data or an augmented feature set or whatever. And then I think it's important to keep in mind what is meant by zero shot and few shot. That is just counting the number of examples you hand to the language model in the instruction or in the prompt before actually asking it to fulfill a task. So I brought okay, it's German, but I think you understand. The task is to translate from German to French. So zero shot means I do not give an example. I just say, give me the translation of Käse, so cheese in English. And in a few shot, I give some examples. So that will come in interesting later when we look into the structural agent. So that was in context learning, and the other one is called named entity recognition. And a fun thing is that before LLMs, named entity recognition was a big deal, so to say, because there were a lot of efforts going into models which are able to extract information from text, for example, or images. Here I brought an example. So an entity would be, for example, the length or the height or the type or the material. And that is encoded here in an example that could be encoded in a text. So before, one had to train a specific model showing it examples. And with the LLM being able to do this in-context learning and being pre-trained on a vast amount of data, named entity recognition is very likely to be successful. And we will rely on that for a first test. So I think that we got the nomenclature right, and now let's look into what is an agent. An agent consists of mainly three parts. The one in blue, that is the agent itself. So we will see that it gets a bit more complicated, but just to understand the concept. So the agent itself contributes or is composed of different parts. The one is the LLM, which you can see here. And then we have some memory that could be the states of that LLM and so forth. And we can provide some objectives, we can define some actions, and we can get some feedback from outside. So that is components which we can assign with an agent. And very interesting, I think, is that there in this concept is the ability to have tools that could be, for for example, a chat, that could be a machine, that could be a software like steered over the APIs, or a crawler for getting content from, example, the web. And the third part is an environment where this agent interacts with. So that could be a game, a simulation, that could be the real world in the case of the machine, for example, and so forth. We are seeing agents, or these kind of agents, since I would say a year or max 2, at least in my knowledge. And I brought this timeline here, so 4,000 years with the abstraction and the formalization of the matrix methods, 100 years of computational and numerical method development, and then roughly 20 years or so in the actual newest wave of AI with the deep learning. So you see an immense speed up, and now we are at the edge of these agents, and my guess is that we will see that in maybe 5 years or so, given the speed of what the current development was. And that gave rise for me to look into that if and how we can use that for doing structural analysis. So as you can imagine, the world is a bit more complex than this abstract figure, and I just want to make 2 points. So the one is an agent is something different from a workflow. A workflow is I can give an input and then maybe connect 2 LLMs to do something via a prompt and then generate an output. It would be called prompt chaining. And I can have different versions of that, and the thing is that a workflow is predefined by me, so the type of error and how that architecture looks like, that is pre-given by me. With an agent, that's not the case, so I do not predefine workflows, okay? Because the agent should determine its own actions based on feedback which the agent gets from its environment. That could be another software, that could be another agent, that could be a human. And for the agent itself, there is multiple ways of how to lay out this agent architecture. So what you can have is very simple reflex agents up to hierarchical agents where these things were inspired by actual teams in a company, when you look here. So there is something like a supervisor agent, and then we have a researcher agent, searcher, web scraper, whatever. And the research hypothesis now is that we look into different kinds of these architectures with the view of our 3 main structural analysis tasks from the beginning, and how people actually work in an office, right? That would be maybe more this hierarchical agent style, because the tricky part is to come up with the instructions, with the role description of that agent. Due to time, I don't want to go into a lot of details, but I want to show first results or first things to be discussed. So what we did at the moment is to abstract a couple of agents, and roughly you can think of, at least in my understanding or my opinion, we need at least 2 agents. The one is the structural analysis agent, fulfilling the first core principle of model abstraction. And a second agent does actually the computation. And you see immediately where I'm heading to with these tasks. So I think it makes sense to assign different agents to the different tasks, because they have specific things, specific targets, and specific layouts to be implemented in them. For example, if you look to the very left, it makes sense that we have a structural analysis and this Baustatik agent as the modeler, because this one I would have to feed all scripts which I have heard at ETH, all books which are out there, all knowledge of the company maybe. This itself is a research topic which is complicated, and I don't go into details here, but that would be like our brain, right? The other thing is why we split away the RFEM agent as one type of finite element method agent is that the set of tools and the set of knowledge which this agent needs is completely different. Because this agent just needs to understand the code basis of FM. And maybe you give it a documentation. And we will see that there is distinctly different approaches to embed this kind of explicit knowledge in books and plans and whatever. And this differs from embedding the knowledge represented in a computer code. And yeah, I bring you two examples, as I said, given the restricted time. So the first one was to investigate a predefined workflow for an agent which takes some user input and a task to come up with a structural FM model. The modes were textual input, images and voice were the voice. I just took my textual description, which I handed over to the language model, and I just spoke it into the PC and used that as the input to the LLM. And you will see, and that is the outcome of that research, that there is three key components. So the one is the prompt engineering, like the instructions of what this agent should do, like what's his role and task. And then, as we are looking at this code agent, so to say, the FM code agent, this structured output generation and the pedantic data validation, that is things which are different from the knowledge from the structural modeler agent. And we will see why that is. So let's first go into this step of a prompt template. So this is where I tell the agent what to do. I brought it here. That is not a function at all. That is just a first simple instruction. Hey, you are an FM agent. You extract from a given input entities, which are the geometry, sections, members, whatever. You can read it. You would be able also to give some few short examples here on, for example, how you define a column or a slab or whatever. But the idea is to have this separation of tasks. So this guy does not have to know what a wall is, because that should be the task for the structural agent. And we will see how that works in an interaction. So that was the first part, and so that was my biggest learning in that creation of the agent, that the language models, if you remember, a language model is a probabilistic model generating probability or words with a certain probability. Now you want that this thing should produce a deterministic computer code. What happens if that generates text at random? Code will not run because the computer code, the FM model, the finite element script, that has to be exactly 100% in line with what this finite element code needs. And how did we solve that? So first we said, what is the steps, what is the components of a structural analysis input file in terms of a finite element code? And you see that here, first there's a section on defining materials, the sections, the thicknesses, nodes, lines, members, surfaces, supports, loads. And for people in the LLMs, that is different from giving all that as a prompt. A prompt would be imprecise because I could not guarantee that I have, for example, different data types ensured. Okay? So that is, this data validation, I think, is one necessity to ensure that the outcoming finite element code, that could be also a cut code if you want, that has to be 100% deterministic and 100% sticking to the definition of how this software wants to see its instructions. Okay, and that also means, so this is, so to say, reflecting a bit the engineering sections of the finite element method input file. And this one is just rewriting the code of the finite element method with, we used pedantic in that case. And you see it here, so I inherit all the classes which come from the FM. I inherit from the pedantic base class. So let's see some results. So what did I do? I gave some text, like design me a concrete beam with a cross-section. gave some input on the length and the load. Yeah, different things. So that is beam structures, that is walls, slabs, and so forth of different complexity. And then I also put some images. And my idea was, okay, what happens if I just have a sketch? Because that's maybe what people would like to hand into that, or what happens if I have an actual plan. And as I said, for the voice input, I just spoke the text and gave that voice file, that VI file, to the multimodal language model together with these pedantic classes and so forth. An interesting thing here is that if you think of creating a synthetic data set for such kind of problems, there is no method on coming up with feasible or useful examples. If you have a parametric model, for example, the width and the height of an object, sampling is easy because you vary the width and the height to a certain step size. How do you vary the complexity of a structural analysis model? So I just came up with two new measures, which are really simple and to be discussed and refined, to stratify the generation of examples where we can test the geometric complexity on the one hand side and the structural complexity on the other hand. Okay, and I just used the sum of the vertices as geometric complexity and then just the sum of loads and supports. So I know mechanically that's maybe a crime, but you know, that's the first measure of dealing with complexity and having differently complex things to be quantified. So what do I evaluate? Computational complexity, meaning how many approaches it took the model to come up with a final FM code, the time it needed. And then I invented a performance measure I called intention fidelity. It is a judgment by me on a Likert scale from 0 to 3. And the idea was just, how can I measure the correctness of a generated FM code to what I, as a civil engineer, would have done in that code? So there's different approaches. You could just take the embedding of that code, that will be a vector, and then compute the sum or the difference of these two vectors. I said, hey, I'm a civil engineer. I want to look at this code and then give a rating if that has done the job or not. But as I said, that's all preliminary because there is not really an existing measure on coming up with the problems in terms of sampling and then evaluating them. Okay, so let's see some results. What I found interesting is that the input modality was significantly influencing the success of that method, where the text was on average the best one, but with a big scatter, as you can see here. And I think the audio comes in second. And one could conclude from that if you want the model to be fast and successful, then use a text input to that. And for the images, they did the worst job, even if the complexity of the examples were similar. And I think that is a bit of a problem of dimensionality, because the image, that is like a matrix to the language model, and the text is just a couple of strings, right? Yeah, so that was some results, and then I can visualize some things. So as I said, these text examples, they worked best. Here, simply the beam, what was created from just this text. And if you look at this image input, that was even worse than my textual description of that wall slab with the cutout of the door. And when looking at these generated files, some other funny observations occurred. That, for example, even if I instructed in my prompt, hey, a civil engineer wants to model his geometry in the z-axis always opposite to the positive z-axis. So the wall, if I say a wall is 5 meters high, I want that this 5 meters goes into negative z. I did that in the prompt, and still this model ignores that. Yeah, so that was another learning that prompt engineering obviously is not strong enough to be able to that. So how do we go further with that? Here, in my eyes, the outcome is, okay, like what an engineer would know from his training, from the lectures, that, for example, a modeling convention is that we model in the negative Z direction a wall and not the opposite, even if we don't say it explicitly, or what a wall or a slab at all is. Yeah, that this is not yet integrated in that one for the sake of being task-specific as a translator. So the remaining task is to come up with this structural analysis agent who understands some domain knowledge, which we feed by books or the lecture notes. I want to show two examples. The one is a geometry agent. So our Baustatik agent, our structural analysis agent, actually is a family of agents with different specializations. And one is to extract the geometry, because that on its own is complicated enough to be done right, as we have seen in this first workflow agent, reflex style agent. So what do we do here is we have an input. We give the system prompt, like you're a geometry agent. Then we give a text or an image, and we provide tools that could be a human feedback. So I can type on my console, and we implement an observer, which is simply another LLM, and a coder, which is another LLM, but with instructions on having a specific task. For example, the coder is an LLM just doing codes and refuses to do other things, and the output of that is lists of points, components, lines, and whatever. And to go a bit into more complex structural systems than the ones I showed, and that this actually works with the specialization, I brought this very dense slide. So the idea is that we feed it some, for example, image of a hall which I want to model. And this has not the task of modeling it in RFEM, as I said, so they do the task sharing. This one has the task of just coming up with the geometry and allow for intervention by either the human or the observer. So the observer, as I said, is another LLM. And what we do is the agent, so to say, is the steering entity. And you see it here in the chat. Okay, the agent first says to the observer, hey, here you have the input. What kind of components and geometry do you see in that picture? The observer answers, the picture shows whatever, and you as a human can read that protocol and intervene at any point. In the end, what we want to do is have a parametric definitions of that node, because as a human, I would know, hey, I want to generate this hall in a parametric fashion. And that would be my advice or input to the agent. And then, as I said, the last step would be generate me either the Python code to do that geometry, or give me, here we said, give me the definitions of the parametric nodes. So I have the formula, and as I said, you can task or ask for whatever you want. Yeah, and if you check it, so actually that does the job. And if you look to the left, I was specific with the framing space and the inclination of the roof. And during that analysis, if there is some uncertainties about you forgot to prompt a geometric dimension, the observer would tell you that, so that he cannot, or this model cannot find, for example, the width of the hall span or so. So that's I think interesting, because that has a deeper understanding of what's going on. And as I said, my hypothesis is that I think we will see like this whole couple of agents working on these different structural analysis tasks. Another example which I wanted to show you is there's another agent doing the model building, and this model is simple enough that we do not have to argue what the outcome should be. So that is a crane in a hall, and I just ask this agent that it should give me a structural surrogate model, like the first structural analysis task. And as I said, this model is simple enough, so we are not arguing if that is this frame or not. So this is a simply supported beam with a line point load. And yeah, actually it finds that this is the case. And yeah, this thing here that uses also the ChatGPT-4 in the backend as an LLM, but we gave it some civil engineering books for structural analysis, and obviously it learned some things. You can prompt that for even more complicated tasks, like get me a surrogate truss structure for some concrete things, for example. So that is a modeling agent. As I said, due to time, I do not go into more detail. And then the last agent which I want to present is, or we saw it again, this translation of my geometry, of my structural model to the FM code, because that's in the end what the engineer needs. And here we visualize that, and I think that is important, that there needs to be this interaction, right? So the agent that gets some tasks, here it was, so the first agent came up with that model. And then we say, okay, now let's translate me that model into an FM code. And I want to be informed what you're doing. And yeah, here you see a bit of the live script. So you remember this structured output format which we enforce. So we want to know about the geometry. We want to know about the cross sections, about materials, whatever. So it told you what it found as a modeling step and the recognition step, and then it shows you the code it came up with. So you can correct it maybe at this point or instruct otherwise, and then actually you can send or instruct the agent to send it to the actual FM and then compute it. Okay. So what's the quintessence in 1 minute? Remember that I said the past waves of AI were passive in a way of that is another model in our toolbox, but it's still passive. So I have to use it, and there is no bigger implications on my workflows and so forth. So today, okay, that should have gone differently. So today, if here we look at the 3 core tasks of the structural engineering, as you remember from my first slide. Today, the human is very much doing the first and the third one. And 100 years of research went into coming up with new methods in our second core task, the computation and analysis. And I think, and that's my hypothesis to close with, in the future, these kind of agents will be present in all of these tasks. And I think we have to deal with that. So the takeaway is we will see these active components, these AI agents, and we have to interact with them in more depth, which gives maybe new dynamics to the planning teams and so forth. My thing is that they're not replacing the structural engineer. Rather, they are augmenting what we are doing. They are speeding up what we are doing. But as you saw with the intervention, it is very necessary still that a human looks at what this agent did, because the model abstraction, that may be not, that may be not unique. There can be different, for example, truss structures which are in equilibrium, which I can do my reinforcement with. So I think the engineers are not replaced, rather they have a shift in the task what they are doing. They have to judge, to interact with what these agents are doing. And I think we need to spend some research on how we structure these agents and also tell people in practice. Because, for example, Global is trying to get that technology in their software, which means they expose that to people in the future. And I think it is most important that the trajectory of that research, like what we are doing there, that is in line with our core 3 structural engineering principles and paradigms. So I think it's our community to drive that. Yeah, with that, I'm done with my presentation, and thanks for coming. And yeah, I'm looking forward to questions, and then I think there will be some apéro.
For sure, yeah. Yeah, Michael, thank you for this very interesting presentation, this very on the edge of what we know topic. And we're open for questions from the audience. Don't be shy, feel free. But I guess you can also.
Thanks, Michael. Very interesting. So I'm looking forward to have your agent pass one of our structural concrete exams in the near future. Maybe a question. Could you pull up one of the text prompts that was successful in generating a structural model in the end? My question was whether in that text prompt you had one where you said like that 5-meter beam with 30 by 50 cross section or something like that. Because I understand that the text prompts worked best, right? So design a concrete beam with a rectangular cross section made of that and that length, supported, simply supported. I know with a isn't quite some abstraction already in that text, right? So yes. You still need someone to produce that. And is that the reason why then the drawings are less successful?
Yes.
Except that they're a bit not really super sketches, right? So what? But I would expect like the number 9 there, that should be. Should give you the same result as the text number 1, more or less. Well, it's a 2-span girder. So is it that part of the abstraction is already in the text, or are there other reasons?
Yes, I agree, and that was my conclusion. So there will be, if you go to FIB in Antibes, or I can send the paper, exactly that was my conclusion, or the same. I had the same conclusion. So the representation in an image, that is a matrix with, 0 and 1s. So I have maybe 64 by 64 zeros and 1s. And for the text, I have maybe, 50 tokens. So way less complex, more condensed, and exactly what you said from an engineering perspective, already abstracted. So the entity recognition in the condensed text is way easier. There it says concrete. Here it says C5060. I would have to know that this is a convention for a concrete. For me, the hypothesis here was, as you remember, the LLMs are trained on vast amount of data. Nobody knows what this data was. They said we downloaded the internet or so. So my guess was, hey, if there is a chance that such kind of conventions are in the model, is that true, yes or no? Obviously not to a big extent. Which gives rise that we have to come up with our data set, so to say, to feed the LLM so that it understands conventions. Like this is a representation of a concrete grade. This is also text, but this is a representation of the geometry. So we could show in that work that even these LLMs are foundation models, and you can use them for different tasks. They are not much of use for economic applications in structural engineering, because they are lacking our specific data and conventions, which means we have to do that. Because computer scientists, they would also not know that this is the concrete grade, this means geometry, and this is a point load. So that is, I think, a step of research what we have to do, and there exactly we have to work together, because there is concrete conventions, there's steel conventions, there's timber conventions, there is whatever convention. So I think that this cannot be solved by one person. And another thing is what you're pointing to. I call this the structural complexity, which I condensed already in the text to the modeling. How do you come up with a number of judging how complicated that system is compared to the wall, compared to that slab? As an engineer, you would have the feeling, yeah, simple beam, what's the problem? Yeah, that's a wall, that's a cutout. The model, this pre-trained model, obviously does not know that because it has never seen it. Yeah. And this is lacking. Like, how do we measure the complexity of that systems? So is that way more complicated than the single The single plate, yeah, maybe because there is a lot of more support conditions, but in reality, maybe it's not so complicated than a shell or whatever. Yeah. So we need to find like a formula of quantifying how complex stuff is. Yeah, and I think there is no answer. I did search for it really a long time. I did not find it, for even in the cut geometry literature. Yeah. Okay. Yeah. Thanks.
I think Anton was first.
Maybe I don't need a mic. I'd like to challenge you a bit on this, whether we need to solve for that. I also work with AI agents, more in the architectural design and architectural understanding. And then more and more I'm becoming aware that there is a version of the future world where all these annotation systems and drawings that we invented for the previous paradigms are rendered not needed anymore, worthless. And there is a different type of representation, how do we carry out the ability to validate a certain design. So for example, and then I recently read a great quote by someone, I forgot the name, but if it comes back, I'll say it. People don't want drawings, they want buildings, right? So why would I even be in a position to say the cross-section of the beam is 30 by 50? Why not just say, I have this kind of slab geometry where I want people to walk, or there's the bridge. It's much more loosely defined in the way that we interact with the language models as chatbots today, and then they take this more kind of specific. Is that something where you think things are going, or we need to have that artificial almost step of the domain-specific representation?
Okay, so I give a twofold answer. The first one is I also believe that the representations we take here are maybe not the best for the machines. Yeah. These stuff we use because we are used to talk to other engineers in that settings. But for a machine, and we learned it with the language models, they don't care if that's video, text, or whatnot. They see a vector. So I'm in line with that. For me, the thing why this still is present would be how to keep the human in the loop in the decision-making process. So would you accept, I mean, I think that at the moment there's no clear answer, or I would question that I just want to say, give me a slab, whatever. Why? Because I have no intervention. And maybe sometimes that's needed. Because, you know, if I pull away a lot of the constraints, the design solution space is exploding. What does it mean, give me a slab or a building? There's an infinite amount of possibilities. The other thing is, if we rely on just the pre-trained things, we resample what was in the training set. So maybe there's nothing new. Yeah, so for me, I think that the future will be that the computer or these agents, they themselves find a way of representing that kind of information, for leaving the people out and doing their stuff more efficiently, but that we still stick for the communication with the engineer or the architect to things which people are used to, which they can imagine, which they have used, right? Can be maybe changing, but I think that the model abstraction, at least in the structural engineering domain, that will pretty much stick to that, because that also gives rise to check what the agent does. And for me, or for the structural engineering community, I think that checking stuff is very important, because in the end it's about safety and about risking lives and about, do I have to give money to a person if they're hurt? So that simple models usually engineers enable to get a feeling if that's right or not. So I can imagine that you say in the future, design me a house, here you have a box, you can do whatever you want in there, but give me at least the five most important abstractions of the structural systems you have, and point me in your model where they are. And then you look, I see a slab or a wall and whatnot, and then it says, okay, I think this is that, and then you would say, okay, I can relate to that, I believe. In fact, it's my my firm convince. I'm firmly convinced that in the future our role will be more decision making and not mechanically transforming information. So if that is going to work and we solved all this sampling, stratification stuff, how will that look like? It will look like, okay, let's design me this bridge, this house, whatever. It comes up and then it constantly says, hey, I come up with that, I come up with that, I come up with that. What should I do now? So I think that we will see that engineers need to make decisions more frequent, so higher frequent decision making in little time, which in my eyes gives a big problem. How about the unexperienced engineers? How do they make decisions? So, and in the long run, I think that also has implications on the business models we have and how do we teach the students going from the universities who are not experienced in all that stuff. They have an explicit theory foundation of stuff, but there is 80% of the things you see in the office. If you have not the time by doing your models, how do you judge an agent who does the model in a minute or 5? Yeah, so, and
Also second, if you don't do the work, you don't understand what the work is.
yes, and that's why I think this is not a theoretic problem alone. We have to care for all this, how I measure the complexity and how the agent looks like and whatnot. I think that the industry or the, Berufsverbände, they need to solve, or the community has to reason a bit about, hey, what happens? What do we do with the novices in the offices if they are not paid anymore for doing these jobs? Do they get nothing in the first 2 years, like in big architecture companies? Don't know if that's acceptable. Or do we enhance our training, meaning we have 5 years of theoretical study at ETH and then 2 years of practice? And we see it as education? I don't know. I'm just saying that I think this is a realistic future, which we are looking into. And I think the community of architects and engineers, they have to find an answer to that because that will shift how we work.
Michael, thank you.
Thanks for being here.
I would say we will forward the questions to the apero. Maybe you can pull up, yeah, exactly. Those slides, so I would like to draw your attention to the next week on the 15th of May. There, Paula Meyer-Struden is coming by and will give a presentation on modeling the unseen, the future of spatial experiences in extended reality. And maybe some of you missed the last talks, so you have now the chance to rewatch all of them on YouTube, on our YouTube page. And yeah, with this said, thank you. Thank you again, Michael, thank you, and enjoy the apero.
Juhu.